All right, so in this problem, I have a wheel, right, or a thin uniform cylinder of radius 0.1 meters, right? So my radius is going to be 0.1 meters, and this wheel has a mass of 2 kilograms. It is mounted on a frictionless horizontal axle here, as in the figure. Great, we did that. The fact that it says that it's frictionless tells me that I can ignore any sort of um, loss of energy, or I can ignore any sort of dissipative forces like friction in this problem. So we have a light cord, right? A light cord means that I can ignore the weight of the cord, and it is wrapped around the wheel that supports a sphere of radius 0.5 centimeters. So that would be 0.005 meters. And that sphere has a mass of 10 grams, so that'd be 0.1 kilograms. And we want to calculate the angular acceleration, so angular acceleration is alpha, of this wheel. So there's a few things that I need to consider here. Whenever we have an object, like a cylinder that has a cord wrapped around it, I'm going to assume that as it spins, I have no slippage happening, right? The next thing that I want to consider is what is going to cause this wheel to rotate. I have no discussion of any applied force, like it doesn't state suddenly a squirrel comes up and starts pulling on anything. There's nothing here that is obviously going to make this wheel rotate. So because I have no obvious, nothing obvious given to me in the problem that is going to cause this wheel to have any sort of acceleration, I want to consider forces. I also want to consider torque, right? Because I have angular acceleration here, I'm probably going to have some sort of torque applied to the object, right? We have a solid disc, or this uniform cylinder, that is going to be rotating. So this is a rigid body of rotation. So I'm going to have torque, and I'm probably going to have forces here, because some sort of force is going to need to act on this to get any sort of angular acceleration. In order to get this thing to move, some sort of force is going to have to act on it because it's not already in motion. So I want to figure out what kind of torque I need to use here. I cannot use RF sine theta because that's not the torque on a rigid body. So the torque on a rigid body is your moment of inertia times your angular acceleration. This is the torque that I'm going to want to use, which is good because I already have that angular acceleration variable in there. That tells me that I'm on the right track. The other thing that I need to consider is the forces. So the first thing I'm going to do is I'm going to write down Newton's second law, F is equal to ma. And I think that what I want to do now is I want to draw my force diagram. So I know that something is going to cause this object to start rotating. I'm going to have my force of gravity pulling down, and I am also going to have this tension force in the opposite direction. So this tension force is what's going to cause my disc to rotate, is what's going to cause my wheel or my uniform cylinder here to start rotating. So let's see if we can start to solve this problem. So the thing that I want to think about is asking us for the angular acceleration of the wheel. So I'm going to think about the torque on this wheel, and that is going to be I, your moment of inertia, times alpha, or your angular acceleration. And I know that what's going to cause the torque to happen is going to be a force, and this is going to be the force of tension. But force by itself is not equal to torque. So I am also going to have to use this RF version I have no sine theta because I'm not considering any angle here. So I have the force of tension times R. And this R is going to be the radius of the wheel that is the radius of the wheel that is turning. But I can't go any further here because I don't have my moment of inertia. So I need to figure out what my moment of inertia is going to be for this uniform cylinder. So for, what do we have? We have a hoop, we have a hollow cylinder. So this uniform cylinder is the same thing as a disk or a solid cylinder. So I'm going to use 1/2 mr squared. So my moment of inertia is going to be 1/2 mr squared. So I'm going to go ahead and plug this in for my moment of inertia. So I have 1/2 mr squared times alpha is equal to the force of tension times the radius. I've used all of these capital letters here because this is the mass of the mass of my wheel, the radius of my wheel, the angular acceleration of my wheel, and then this is also the radius of my wheel. So I see that I have the force of tension here. So I need to find a way to come up with an equation for my force of tension. And to do that, I'm going to use the force diagram. So I have the summation of forces in the y direction is going to be my force of tension plus the force of gravity, and this is going to result in some sort of acceleration. Now, this is just the basic equation. I'm now going to take into account directionality here. So I have my force of tension, that's positive, minus mg, right, because the force of gravity is going down, and that's going to result in a negative tangential acceleration, right? Because if I think about my y coordinate, the object is going to be accelerating in the negative direction. So I'm just going to rearrange this equation so that I have the tension by itself. So I'm going to plug this in for my force of tension, and that gives me 1/2 mr squared alpha is equal to mg minus m times my tangential acceleration, and all of this will be multiplied by the radius of my wheel. And this makes sense because the radius of the wheel is going to determine how quickly the object is translating in the tangential or negative acceleration direction. How fast it is moving downwards is going to be determined by how much string is coming off of this wheel, and that's going to be determined by the radius. So you can think about that like if I have a spool of thread and I pull it with the same force as I do a hose that's wrapped up, the spool of thread is going to move significantly quicker in the negative direction because the radius of the spool is significantly less. The next thing that I see is I have another issue here. So I see that I have an angular variable on the left-hand side, but I have a tangential variable on the right-hand side. So I need to convert my tangential acceleration into angular acceleration. So to do that, I'm just going to replace my tangential acceleration with r times alpha. So that means I have 1/2 m capital R squared times alpha is equal to mg minus m times r, but it's going to be the big R because the tangential acceleration is not dependent on the radius of my ball that's falling. It's dependent upon the radius of the disk, and I'll multiply that times my angular acceleration, and then I'll multiply it times r again. The next thing I need to do is I need to get both angular accelerations into the left-hand side, so I'm going to have to distribute the right-hand side of this equation. So I have 1/2 mr squared alpha is equal to mgr minus mr squared alpha. And then I'm going to add mr squared alpha to both sides. So this 1/2 capital M r squared alpha plus lowercase m r squared alpha is equal to mgr. The next thing that I can do is I notice that I have r in all of these. I can cancel out one of the r's. So I can divide all of this by r, and I'll end up with 1/2 mr alpha plus mr alpha is equal to mg. The next thing I want to do is I want to pull my alpha out because that's what I'm solving for. So I'm going to want to get it by itself. And then I'm going to divide both sides of this equation by the term that's contained in my parentheses here. So this is going to be alpha is equal to mg divided by 1/2 capital M, sorry about that, capital M r plus lowercase m r. The other thing is I don't like to have fractions within fractions, so I am going to redistribute that. So I get 2mg over capital M r plus 2m r. And now we should have all the information we need to solve this equation. So the mass of my sphere is 0.01 kilograms, and g is 9.81 meters per second squared. And I'm going to divide this by the mass of the wheel, so that's 2 kilograms, times the radius of the wheel, so that was 0.1 meters, plus 2 times the mass of my little sphere, and times the radius of my disk here. So let me do some real quick dimensional analysis to make sure that I'm on the right track. Kilogram meters second squared over, these are both kilogram meters, so this will end up with 1 over seconds squared, so this will be radians per second squared, and that is the unit for angular acceleration, right? So I know I'm on the right track. So now I'm going to just plug this in the calculator. I'm going to turn on the calculator, and then I'm going to plug it in the calculator. And I get a solution of 0.97 radians per second squared. I don't really have a way to determine if I think that this is a realistic answer or not. But because I did this dimensional analysis, I feel fairly confident that our solution is correct.